Good morning, everyone, or good evening if you're joining us from somewhere in the Americas. Welcome to the fifth webinar of the Kyushu University SEG student chapter. My name is Henrik Udri. I'm a graduate school student at Kyushu University, and I will be your main host today. It is a great pleasure to introduce to you our guest speaker today, Professor Antonio Arribas. Professor Arribas is from the University of Texas at El Paso, where he is a professor of geological sciences. Professor Arribas holds a bachelor's degree and a master's degree in geology from the University of Salamanca in Spain, as well as a PhD from the University of Michigan. Following his PhD, he worked as a postdoctoral researcher at the Geological Survey of Japan. Professor Arribas also has more than 20 years of experience in the mineral exploration industry, where he, among other positions, worked as Vice President of Geoscience at BHP Minerals Exploration, Senior Manager of Geosciences at Newmont, and Exploration Manager South America at Placer Dome. Until recently, he taught at Akita University in Japan before moving on to the University of Texas at El Paso, where he is now the Kenneth F. and Patricia Clark Distinguished Chair in Economic Geology. Professor Arribas is also past president of the Society of Economic Geologists. The title of his talk today is Magmatic Hydrothermal Systems, Science and Exploration. After Professor Arribas' talk, we will have roughly 30 minutes of questions and answers. If you wish to ask a question, please make use of the raise hand button available in Microsoft Teams after the talk. We will then call on to you to ask your question. If for some reason you can not use your microphone, please type your question into the chat and we will then later read it out to you. So without much further ado, I will leave the stage to our guest speaker, Professor Antonio Arribas. Thank you very much for coming today.
Hello, I guess you can hear me right this time.
Yes.
So it's a pleasure to be in contact with you guys in Japan again. I left Japan only a year and a half ago, and I have to say I miss it very much. Okay, so some of you in Akita, or some of you who are in Kyushu that were in Akita before, have seen some of these slides. So yes, we were. I think am I sharing my screen?
At the moment, I cannot see your screen. I think you should be able to. Let me see if I can. Ah, yes, now we can see your screen.
Okay, very good. So, David asked me to talk about this topic, magmatic hydrothermal systems, and I gave him a couple of options, or 3 options, and he chose this one. So I'm happy to give this talk. I'm going to talk about magmatic hydrothermal systems and the type of ore deposit that happen within these systems and the connection to volcanoes. So I will first start with a little bit about the science from the perspective of studies I have done in my career, and then some talk about the exploration side. More than anything else, some anecdotes about exploration in this environment and lessons for exploration. But in a 45-minute talk, there isn't much time to go over. It's too many things to cover. Okay, so when we talk about ore deposits, magmatic hydrothermal ore deposits and volcanoes, the key common ingredient there is water. Sorry, I'm talking in Spanish. Is water. Magmatic hydrothermal, but it's magmatic water. And there is no question that when you see an eruption like this one of Mount Pinatubo in the Philippines in 1991, there is a very, very large amount of hydrothermal fluid in the form of volatiles that are breaking up, are expanding and breaking up what would have been a more normal magmatic eruption column. So there is a lot of water in these systems. I'm going to show you a small video. Turn off the sound. A small video of a volcano a few years, 6 years ago in Chile. And this is a high speed over a few hours actually. And you can see really that what is happening here obviously it's a volcanic eruption, but it's really water coming out of the Earth's crust. Is water coming together with breaking rock, breaking volcanic rock. And the key here is that water, which is capable of transporting metals like copper, gold, silver, zinc, etc., leaving those metals behind instead of releasing them into the atmosphere. Okay, that is the key to form these deposits. So where is that water coming from? Really, that water, like any hydrothermal deposit, the issue of source, transport, and deposition is really the basic concept. And the source of that water, in large part, is seawater. Seawater that has been present in the hydrated oceanic crust, and as the oceanic oceanic crust is subducted in a subduction zone, it will be heated, and there will be dehydration, release of that water, and that aqueous fluid, which is rich in chlorine and sulfur coming from both the mid-ocean rich sulfides as well as seawater sulfate, and is oxidizing, this will generate a partial melting of the mantle wedge, and these partial melts of the hydrated mantle wedge will start generating magma that will keep ascending and slowly turning from a mafic magma to more intermediate compositions in the volcanic. This is the typical volcanic arc for intermediate magmas. And they accumulate as in the form of a batholith a few kilometers below the surface. So this is the environment we want to be looking at. The batholith, this magma chamber, which is typically is going to be recharged from time to time from below. And within the magma chamber, there is solidification, crystallization. Aqueous fluid is not, it doesn't want to go into minerals. I mean, it will go into some minerals, but it will be a residual aqueous fluid that will keep concentrating some metals. And the key parameters here is to focus the fluid flow and to do a series of physical chemical gradients to the fluid, especially physical gradients to the fluid, very sharp physical gradients to the fluid that will lead to the deposition of those metals as sulfides and other minerals. And this comes together with a lot of water, comes together with alteration of this column of rock. We are talking about a few kilometers here. So this is essentially what we want to do. A low-grade concentration of copper, for example, in a magma chamber, in that pluton, concentrated into, just like you would do into opening a bottle of champagne, and help it deposit those metals. And at ETH in Switzerland some years ago, they brought this very, very interesting, very nice paper where they model how the magmatic fluid leaves the magma chamber. Here there is the magma chamber. We are looking at this portion of the diagram, and it has waves of overpressure fluid that creates huge permeability changes, very large permeability changes of the order of 2 orders of magnitude, and that produces a kind of very special rock that it looks like this. Is a typical rock that happens to be in this environment, in the porphyry copper type deposit. It's a stockwork veining. Many, many generations of cross-cutting quartz veinlets, and also with very intense wall rock alteration, like here, this white alteration is a white mica, and precipitation of metals. Okay, so in a slightly more complex diagram, but still very simplified and very useful for understanding and for exploration, this is the diagram by Dick Silito of 2010, summarizing magmatic hydrothermal system under the broad term of porphyry copper system. And one of the things I really like about this diagram here, with the colors reflect hydrothermal alteration. You can see that there are many different types of colors, and all the way from deep within the magma chamber or close to the magma chamber to very shallow. This alteration reflects different temperatures of a reaction of the fluid with the wall rock. And in a pH versus temperature diagram similar to this one, we can see that it's just the fluid path is easy to recognize. It's a high temperature alteration like K-feldspar or secondary biotite, which we call potassic, to an alteration consisting of white mica, which we call here sericitic or chloride sericite, then pyrophyllite by cooling, further cooling of a muscovite stable fluid, and into a kaolinite dikite, which is the upper part here, the advanced argillic part of the system. So these alterations are extremely important when it comes to exploration because it helps us go to the deposits, to where the deposits are located. The deposits, the ore bodies here are not that easy to see. Silito produces another figure with just the ore bodies, which is this one. So they are colored most in red, for example, the porphyry copper environment. This is the same bell shape. This was the same volume of rock that was being subject to those waves of overpressure magmatic hydrothermal fluid. The porphyry copper typically with a bell shape, with different kind of shapes, but typically something like this, surrounding the intrusions, the dikes and intrusions from the magma chamber. Skarn or carbonate or the replacement deposits, if there is an appropriate lithological unit like a carbonate that is prone to this type of alteration and special mineralization. And then above this, about this level here, we are talking about the epithermal level of mineralization. So within 1.5 kilometers of the surface, of the paleosurface. So epithermal and porphyry environment. When epithermal term was introduced in the 1930s, that's many, many years ago, they would have called this mesothermal environment. But today, just for convenience, we use the term porphyry because it reflects very specifically to this type of deposit and now to this type of mineral system, and epithermal because it is a convenient way to talk about shallow hydrothermal deposits that are commonly associated with volcanic rocks or subvolcanic rocks. And then we'll see that there are different types of epithermal deposits depending on the chemistry, on the evolution of the fluid, like intermediate sulfidation, high sulfidation, etc. Okay, so let's go now more to the deposit type. We said porphyry and epithermal deposits are maybe part of a porphyry type system, a magmatic hydrothermal type system, and there is no question when you see this map that these deposits are related, associated with convergent margins, with subduction zones around the world. So the Pacific Rim is an active subduction zone for the most part, but something like here in the eastern United States is a subduction zone that occurred in the lower Paleozoic, when there was a collision between these two continents here, these two tectonic plates, or other belts of porphyry and epithermal deposits are associated with convergent margins and subduction zones in the past. Economic significance of porphyry copper system is huge. So this is a quick summary. More than 70% of the world copper. Same thing with silver and gold, essentially. Gold 60%, but silver more than 60-70%. A large part of molybdenum, almost all the rhenium, it comes from porphyry copper deposits, in addition to many other metals that are produced as byproduct, like selenium, tellurium, as byproducts as a copper refining, zinc smelting. Many of these elements are also produced within magmatic hydrothermal systems, not necessarily exclusively the porphyry type deposit, but maybe epithermal type deposit. So I'm talking about magmatic hydrothermal systems at deposit that form from hydrothermal fluids with a magmatic input, and they may not always have to be porphyry and epithermal. They may be just epithermal, they may be mostly porphyry, etc. So I'm going to use 3 examples of deposits I studied. First one, this was Rodalquilar, this one here, and the erosion, very schematically, the erosion level of these 3 deposits. So Rodalquilar was an epithermal deposit from here to here, from about here to here, entirely within the epithermal domain, touching the roots of the epithermal domain, and it was what we call a high sulfidation deposit. It's in the south coast of Spain. This is the southeastern coast of Spain. This is the Mediterranean Sea. We are seeing a caldera here and a volcanic field about 11 million years old, Miocene age, covered by these are coral reefs, It was kind of a tropical environment with volcanoes, coral reefs. And within this caldera, there are these fractures here. And what we see in these fractures is a lot of alteration, a lot of advanced argillic alteration, which is formed by a very large amount of volcanic gas mixing with groundwater. So in a geological map, we have this very large caldera, oil, about 8 kilometers in diameter, not that huge. And then a smaller collapse feature in the center, a nested caldera inside the large caldera. These units, these volcanic units in red are volcanic domes that intruded mainly along the margin of this caldera and also in the middle of the caldera. And then this pinkish unit is the ignimbrite sequence that was sourced from this caldera, Rodalquilar. Anyhow, there are many deposits, as you can see here, all of them epithermal, some in the core here, in the core of alteration, of most intense, most acid alteration, are of what we call the high sulfidation type. Others, like here and farther away from the core, they are intermediate sulfidation type epithermal deposits. When we look at the very intense alteration in the center of this caldera, along those structures, we find this rock. And many of you know this very well because you are working in an environment in a country with volcanoes, volcanic gases, and these minerals are very common. Others might not know that well. What we see is a rock made up of quartz, alunite, dikite, kaolinite, pyrophyllite, and alunite is this pink mineral here, replacing feldspar and lithic fragments. It's a hydrated potassium aluminum sulfate. And we see another type of rock, very interesting type of rock, that where there is a more intense, more acid stage of alteration compared to the quartz, alunite, kaolinite, dikite, and it's a vagisilica, residual quartz. It's a rock, a residual silica-rich residue from alteration by extremely acid fluids. Extremely acid to the point that they are acid enough, low pH enough to leach even kaolinite, dikite, and alunite. So that requires a pH of 1 or less than 1 at the temperature, for example, of 250 degrees Celsius. So this is the genetic environment of this type of rock. We have magmatic volatiles like water, CO2, say volcanic emanation, volcanic volatiles, maybe 85 to 95% steam and 15 to 5% CO2. And then there can be large amounts, a few percentage of SO2, H2S, HCl, even HF. Those are typical volcanic volatile gases. And some metals are being injected. Well, these gases, these volatile phases, SO2 is going to be critical because SO2 is going to react with water and produce sulfuric acid as well as H2S. This sulfuric acid will dissociate and will produce a very low pH. In addition to the sulfuric acid, HCl from here will also dissociate and produce help bringing down the pH and very acid fluids, to the point that at some point here, where we are getting below 300 degrees, this reaction starts to happen around 300 to 400 degrees Celsius. We start getting extremely acid fluids, a pH of less than 1, and that's where we get this famous rock, the vagisilica, the residual quartz. It's a very porous. Initially, for example, in this case, initially the rock had very large orthoclase, K-feldspar phenocrysts, very, very large, several centimeters across. This is from a deposit in the United States called Summitville. And those phenocrysts of K-feldspar are altered first to kaolinite. If the fluid is more acid, goes from kaolinite, it's replaced by alunite. And if the acidity is even stronger, alunite and as well as dikite kaolinite are soluble, and we leave behind a big hole. Now, this rock is going to be permeable, and this rock is going to be very interesting because it's going to host very often a mineralization, metallic, gold and silver metallic mineralization later. And this is what we see at Rodalquilar in those workings. So we see the very high grade, which the old timers used to work along these galleries, and the low grade that was mined in an open pit. And when we go to these structures, what we see is vaggy silica residual quartz surrounding a fracture. The very acid hydrothermal fluids were ascending along this. This is the conduit that probably may have reached the surface into fumaroles, in very acid fumaroles or very acid hot springs, and producing all of this wall rock alteration. But the mineralization in this specific case, there is low-grade mineralization here, but the high-grade mineralization is inside the conduit. It's an amorphous silica, which has been oxidized for the most part now. This is an amorphous silica. You can see the bedding, the layering of the amorphous silica with black, very fine-grained sulfides. All of it has been weathered later, oxidized, and now is turning into red colors for secondary iron minerals. But that's where the high grade is contained in this type of deposit. And the other type of high grade in this type of deposit, the highest grade, are hydrothermal breccias that clearly include fragments of what is a residual silica. So it was alteration in the wall rock by very acid fluids, and then a hydrothermal breccia happened. At some point, there may be many stages of brecciation. This is a very, very dynamic environment with a matrix of quartz, chalcedony. So mineralization, the gold mineralization in this case is a gold telluride. This is the original, this is the primary mineral, calaverite, a gold telluride. The calaverite precipitated right after brecciation. So there is the breccia, lithic fragments in the breccia, and the massive decrease in pressure led to the precipitation of sulfur. Of gold. Okay, let's go to another example. So we look at Rodalquilar, which is the epithermal deposit here. The veins surrounded by advanced argillic alteration consisting of vaggy silica, residual silica is the same, or silicic alteration is another way to call it, surrounded by quartz alunite, quartz kaolinite, different styles of what is very simplified, in a simplified manner, called advanced argillic alteration. So let's go to higher up in this kind of system. We are going to go to, higher down. We are going to go to Lepanto. We're going to go from the epithermal down to a place, at least one place in the world where the epithermal deposit, the high sulfidation deposit, transitions into a porphyry. So we go to Lepanto in the Philippines, in the mountain province. It's a very large topography. There is a land in this area with a very rugged topography. There is this land airstrip for the mine. Is the airport for the mine, for local mine. They used to remove the gold from the mine, flying out on planes from this small runway. But it's very strange that you see that in this very rugged topography, there is a flat area long enough to build at least a 1 kilometer runway. So why do we have that? Why do we have this flat area? Well, the reason is, if we look at the long section, the flat area is built here on top of a tabular body of silicification of silica, of residual quartz and silica, this dark red color, and silicification associated with advanced argillic alteration, quartz, alunite, pyrite, dikite, kaolinite, etc. So what we are seeing here is fluid coming from this porphyry from this intrusion, moving along an unconformity, moving along a fault. This is the plane of a fault. The Lepanto fault is a long section along a fault, and moving up along the fault, and then finding an unconformity between this lower unit and this volcanic unit, and flowing along this unconformity, typical hydrologic gradient, and mineralization happening here inside this body of very strongly altered rock. So the original place where one of the original places where this mine, Lepanto, was mined over a century ago, is here in a cross section, is in a creek that is essentially a cross section like here, and that's where you see this silicified tabular flat body of silica, copper mineralization, residual quartz, etc. If we do this cross-section, we look at this cross-section here, this is what we see. The Lepanto fault, the main plane of the Lepanto fault, fluids have been going up, the magmatic hydrothermal fluid has been rising along the fault and then flowing laterally along the unconformity. For the most part, that's the dominant control. This vertical steep control along the fault and a low angle control along the unconformity between this unit in darker blue and this unit in gray or light blue. And what we see is the fault itself is another hydrothermal breccia associated with the ore associated with the fault, another hydrothermal breccia from, again, many events of hydrothermal brecciation, very, very dynamic system, and precipitation of copper sulfosalts like energite, like leuconite. This place is the type locality of leuconite, surrounded by advanced argillic alteration like residual quartz. Here is another kind of baggy silica, you see, with the phenocryst all leached out. In this case, they are decayed. In this case, they are all removed. They are dissolved completely. And if we look at the long section now with, at the long section on the right side of the long section with the alteration shown, we see the same thing I was talking about before with the silito diagram, where you see a continuum of alteration from the high temperature potassic alteration in the porphyry. We call this far southeast, FSC, because it was in the far southeast of the Lepanto deposit, sericite chlorite, and then different assemblages of more acid alteration like quartz alunite, baggy silica, and there is a zone of pyrophyllite in between the sericite, the white mica zone, and the advanced argillic alteration. We look at the age of this deposit, and we found out that even though there are many different, small, if you look in detail, there might be many details, but in a broader picture, what we see is two main events. One is alunite, here, this mineral dated alunite from this area here, and biotite from the porphyry at about 1.4 million years. And then the white mica, which this is potassic alteration overprinted by white mica. The white mica about maybe 100,000 years younger, about 1.3 in average million years. So two stages, the potassic and white mica stage, 1.4, 1.3, and the potassic contemporaneous with alunite here. Why? Because the fluid, the high temperature fluid from the magma chamber is at too high pressure for the too high temperature for the confining pressure, and it separates. It separates into a vapor phase and a liquid phase and a brine. The vapor takes with it sulfur that helps produce all this alunite on top, and acid alteration. The brine stays behind at high temperatures and produces the potassic alteration. So it's a phase separation of a high temperature magmatic hydrothermal fluid. The ages of those alunites, like this sample here, are these red squares. So this is age 1 to 2 million years, and you can see that the alunites they cover a span, but the average is about 1.4, which is very similar to the average of biotite from the potassic zone, these green triangles, green rhombohedrons. And the ages of white mica are these blue circles, and they are slightly younger, the average age. Again, you can see in detail, you can see many. It's a very dynamic system, and there is also analytical reproducibility issues. But broadly, we can find those two events. If we look, people look at the fluid inclusions, and they look at fluid inclusions, for example, in energite. This was Mancano and Campbell some years ago already. This is when I was in Tsukuba, at the Geological Survey of Tsukuba, with Jeff Edenquist and Matsuhisa, Watanabe, Sensei, etc. And Dan Mancano looked at the fluid inclusions in energite with infrared microscopy, and this is what he found. From the closest to the porphyry, highest temperatures, around 260, 250, going down to less than 200, a couple of kilometers to the northwest. So a gradient cooling towards the northwest. If you look at the fluid inclusions within the far southeast domain, within the porphyry, fluid inclusions in quartz with early veins, early anhydral quartz veins in ductile veins with the potassic alteration with biotite, they were high temperature, 500 to 550 degrees Celsius. And quartz in fluid inclusions in hydrothermal quartz associated with the white mica, with the sericite stage, they were much lower temperature, 350 degrees to 300 degrees. So what we have is, again, the high temperature stage, potassic stage, at the same time as the alunite is happening here, the acid alteration, the baggy silica and the alunite. The brine goes as far as about here. This is where you don't see any more fluid inclusions with the brine component. So it's vapor versus vapor only, almost, versus brine below. And then the system cooled down as the magma crystallized and the isotherms kept going down towards the magma chamber. And we end up with the white mica stage at around 350 degrees and 350, 300, 250, 230, 220, 200 and less, cooling. So as the fluid ascended and then moved laterally along the unconformity and low hydrologic gradient. And if we look at the stable isotopes in a hydrogen-oxygen isotope diagram, you see water in let's look at the reference. So we have the meteoric water line, we have the local meteoric water in this part of the Philippines, and we have volcanic vapor box and water in felsic magma. So there are three boxes here. This is the water in felsic magmas, the volcanic vapors, which are about 20 per mil with respect to hydrogen, have fractionated, and the residual water, the left behind by the gas magma chamber, which would be even heavier in hydrogen. Okay, so what do we see with the minerals? We see that the biotite in the potassic zone is purely magmatic water. That's what we see from measuring biotite water in biotite at this temperature, assuming this temperature for crystallization from the fluid inclusions. What do we see for alunite? We see a trend from essentially pure volcanic vapor or volcanic vapor condensed into magmatic liquid to a mixture of volcanic vapor and groundwater towards the northwest. So from the southeast, from the core, from the potassic, from the far southeast ore body towards the northwest, decreasing increasing meteoric water component. If we look at the white mica stage, so again, this was the vapor, this was the brine, the green. If we look at the white mica stage, we also see a trend from magmatic water for some of the white mica to some groundwater, some meteoric water mixed with the magmatic water, also in the samples that are more towards the northwest. The pyrophilite, that is a cooling of the white mica, essentially the same fluid, the same composition. It's just a temperature effect. And kaolinite is a bit younger and is farther away also, and that has a larger magmatic meteoric water component. Okay, clear? So this is the model for Lepanto, far southeast. So we have a magma chamber, we have degassing fluid, potassic hypersaline brine left behind, forming the potassic zone, some mineralization, the vapor, the volatiles mixing with groundwaters and forming this advanced argillic zone along the unconformity, the residual quartz, and then followed by this, that was at 1.4, at 1.3 million years, again average ages, but some tens of thousands of years. The white mica stage, the system has cooled down, and now we have a larger degree of mineralization. Actually, in the porphyry copper, it happens with the sericite albite chlorite stage. There is a sericite albite chlorite, and then there is a quartz sericite only. And the sericite albite chlorite stage is responsible for more of the mineralization. This is something that student that visited us at Akita, Michael Calder, is doing his PhD, his master's on this project, and is now putting it together. And that's the conclusion. And the energite seems to be connected to this white mica chloride albite stage in the porphyry. Is the main ore body stage or mineralization stage in the high sulfidation. So let's go now to the third one. The third system is higher up, and we are looking at Akaiwa in Japan. Several of you have visited, especially the students that were in Akita, maybe went with Watanabe Sensei to this project near Hokkaido, near Sapporo. So this is what you see at Akaiwa. It's a Miocene, again, Miocene volcanic edifice eroded by the sea on the coast of the Sea of Japan. And you see chimneys like this one made up of breccia, silicified rock with also residual quartz, alunite, and in this particular case, these white rocks around contain quite a bit of a mineral called suniite. Suniite, which is common in these systems, and it contains fluorine and chlorine, which are again the magmatic volatiles, are trapped in this mineral. It's a silicate, hydrated silicate with chlorine and fluorine. It's suniite. Suniite together with dikite, diaspore, alunite, etc. And if you look more carefully, within there are these silica-rich ridges, and when you look at them in detail, you see the wall rock is residual silica, but there are some breccia, bodies of breccia filled inside. And the breccia, I mean, like a diatreme, and is filled with a sediment, a chemical sediment. This chemical sediment consists of quartz, alunite, kaolinite, even layers of barite. There was a lot of pyrite, you can see, it's all oxidized now. And there is also some detrital the conglomerate that has fallen inside as a deposit, as a detrital deposit, breccia, conglomerate, etc. But part of it is a chemical sediment. And there is, for example, here, next to these figures here, there is this block, very irregular, that when you look at it in detail, the block has sunk. It's a block of breccia that has sunk into a chemical sediment. And you can see the sediment with soft sediment deformation as the block sinks. So this is the tip here of this block. There was a chemical sediment here, detrital / chemical, both, of hydrothermal minerals, quartz, alunite, again, kaolinite. It's like the sediments of at the base of a lake, lacustrine sediments. But they are in a conduit. They are inside a diatreme-like conduit. And this body sunk inside. How do we interpret this? So these are these two. This is the chimney here, or the conduit, probably a fumarolic conduit at depth, and one of these breccias here. And if we, one interpretation is that, again, we were looking at the conduit of a fumarole, and with or a very acid hot spring with this silicification and residual silica, or the roots of a crater lake, with the block having fallen down inside the crater lake, inside the roots of this crater lake, conduits of the crater lake, this chemical sediment. This, by the way, is a gold prospect. It's a high sulfidation epithermal, very small ore deposit, and is surrounded by some intermediate sulfidation epithermal veins. This is equivalent of a sediments in a crater lake like this one in Costa Rica. This is Volcan Poás in Costa Rica. And here we have is the same kind of sediments, detrital and as well as chemical, the same mineralogy, kaolinite, alunite, but here in this case is a volcanic bomb. This is not a fragment of breccia that sank into this sediment. It's a bomb that was ejected and sank in. This is Volcan Poás. This is the crater lake. And that's what we are thinking Akaiwa looks like. It was the paleosurface of Akaiwa. And this could have some of these magmatic hydrothermal systems in the paleosurface could have looked something like this, or, I mean, very variable. It could be just fumaroles, or in some cases, it may not reach the surface. It may be all happening underground, below the surface. But very likely will be something that reaches the surface like this. Okay, and what you see at Volcan Poás from time to time, and this is a photograph from the observatory, the Costa Rica Observatory, is eruptions like this one within the lake. That is the this kind of eruption within the lake, driven by increased magma activity and volatiles degassing, obviously could lead to this kind of hydrothermal breccia at depth. I don't know if it would have to be much larger to be able to do this, to produce this, but this is you can make the conceptual connection between this hydrothermal eruption at the surface and these textures and these sites of mineralization at depth. By the way, this is sulfur-rich, SO2-rich degassing, that color. Okay, so I'm going to move now to the second part, the exploration, and I call this a 21st century mineral discovery tale from east of Java. And what is this? Do you know what I'm talking about here? This volcanic eruption happened in 1883. Obviously, it's not a photograph of a volcanic eruption in 1883 because there was nobody to photograph this then. But probably some of you realize that this eruption is Krakatau in Indonesia, between Java and Sumatra. Interestingly, Krakatau, and this is the poster of a movie that was filmed in the 1960s. This is from the film in the 1960s, before very sophisticated special effects and computer graphics existed. So this is a real eruption from a pool. A real faked eruption. So this is a volcano that they made to replicate Krakatau, and they had a model ship actually moving next to it because there is a love story going on in this ship. And this is the volcano is now quiet. It's not being is not active. And you can see how the model ship, how it was moved along to make it look like it was a slow moving at the time of no computer graphics. Okay, so it's interesting because Krakatau is not in the east of Java, it's in the west of Java. East of Java is this part, this is west of Java. But apparently the producer of the movie felt that people would not go to see, it would not be popular west of Java, it had to be east of Java. Anyhow, let's go west of Java. Let's go east of Java. I mixed that. So we're going to see the volcanic front along the Sundarbans arc. And this is the Java, the island of Java, Bali, Lombok, Sumbawa, different islands. And this is the volcanic front, the present day volcanic front. This dotted line represents the volcanic front in the upper Miocene, say 3, 4, 5, 6 million years ago. And interestingly, a line of porphyry coppers or epithermal deposits occur along this one. So Batu Hijau is a big porphyry copper discovery in 1990 by Newmont. Lombok here, in the island of Lombok, Selodong, this is a large area of mineralization with high sulfidation epithermal structures, absolutely with a forming part of a porphyry systems. There might be 3 of them, and with excellent exploration potential, but it's already a very developed area of Indonesia, so probably not a target for exploration. Then is Bali, and then Tujuh Bukit. And I'm going to go to this one. And again, each one of these is a prospect. Some of them are mines, like Batu Hijau. The other one that just was discovered a few years ago, and it was recently published in a paper, is about another 300 or 400 kilometers to the east. It's called Onto, and it's yet another porphyry copper, another giant porphyry copper deposit discovered along the same upper Miocene volcanic front. So let's go to this one, to Tujuh Bukit, here. This island here. I'm going to finish with this part of the world, and I choose this part of the world because it's it's an ideal place to illustrate the connection between volcanoes, crater lakes, eroded volcanoes, porphyry, and epithermal deposits. It's just a matter of erosion. So we'll see one of them eroded here, and we'll see the other not eroded here. So this is at the coast to Bukit. This is a porphyry type prospect. This is an island, but when you get close to when you go to these outcrops, what you see is a classic stockwork type, sericite alteration, white mica, pyrophyllite, with secondary copper. The copper has been oxidized, the chalcopyrite and bornite have been oxidized to malachite. But this is ore, this is mineralization. Look at this, 1% copper and almost 2 grams per ton gold. This is ore. And that is Pulau Mera, the island, the porphyry copper. And if you go to the east, then we see these ridges up a few hundred meters high, steep ridges made up of silicified rock and residual quartz, just like those Rodalquilar, Lepanto, and many or most other high sulfidation deposits around the world. This is a deposit, the high sulfidation epithermal. This is porphyry. This cannot be mined, of course, because we are in the middle of the Indian Ocean. This has been, they started to mine this for the secondary gold here, for the gold in the epithermal, sorry. Okay, so let me tell you a bit of a story here. I was in Bukit with a company called Placer Dome 20 years ago. And we were fascinated, that's where these photographs come from. We were fascinated to see the porphyry copper, and then we climb and we see these ridges with high sulfidation mineralization. There was a good map, alteration map, and you can see in red is silicic alteration of residual silica. In orange is quartz, alunite, dikite, kaolinite. And there are 3 ridges. And if you look at the gold in the soils, this is gold here. So red is high gold. Clearly, gold corresponds to these residual quartz zones. To this one and to this one, these 2 here. So there was a connection between alteration and gold. So this is the gold we drilled, only 200 meters we drilled. And there was a connection also with resistivity, with the geophysical anomaly, with the resistivity. So both of these ridges, 1 and 2, are silicified rocks, and they produce resistivity highs. So very nice connection between geochemistry, geophysics, type of alteration, and gold. It was 1999, and we were in a rush to leave because the gold price was very low, and we were not looking for porphyry conceptually, to be honest, or even allowed, because the company didn't want any copper. It was a gold company. So we just drilled shallow holes, a couple of 100 meters. And we left with a model where we had the porphyry being the source of the fluids moving laterally and producing centers of residual quartz alteration surrounded by quartz alunite, dikite, with gold along these structures. And the lesson here, one lesson for those of you who are having interest in exploration, is something very important. We drill from above. We didn't drill so much below. So we never really were able to paint this boundary below for the end of this alteration and the end of mineralization. So the lesson here is the absence of evidence below, the absence of evidence here, we didn't have evidence, is not the same as the evidence of absence, of not having something. What happened is, 7 years later, the company, again, the gold price was very low. The company left. Nobody took the property for many years until 2007. And this was the geophysics done by Placer Dome. And we had this high resistivity, these resistivity highs, and there was a large chargeability anomaly below. And by 2008, the model of lithocaps above porphyry copper deposits and alteration is much wider established, much better understood, and a smart group of people doing exploration thought this is a very large lithocap, this has a chargeability anomaly, we have to test it. And they drilled just below the drill holes done by Placer Dome. These were those all drill holes, and the ore they drilled below, and they came up with, for example, here, 700 meters of 1% copper and almost 1 gram per ton gold. So bottom line, there is a porphyry underneath, and underneath this high sulfidation. And bottom line, the age, a PhD done by at Coates by Rachel Harrison, as far as I know, she cannot distinguish the age. They are both contemporaneous. So in this case, there is no barren zone with pyrophyllite. It's directly porphyry to epithermal, a telescope, completely telescope the two systems. These are very old cross-section. They are much more complex today, but they just make the point of very long drill hole intercepts with grade. So one of the largest undeveloped copper deposits was right underneath this hydrothermal, this high sulfidation epithermal deposit. And something that they did also very, very interesting, they mapped with geophysics the magma chamber that is, they interpreted the magma chamber that is below Tungampitu. So with Aeromag, they model in 3D, and this is the magma chamber with different apophyses, different, maybe a dike here, maybe apophyses, but we were above this apophysis magma, which is again is what I was showing before with the disseminated low-grade copper focusing into a point where it precipitates and makes ore. So this is one of them, and this is a very interesting tool for geophysics, I mean for exploration, because you can say, okay, there was one here, there may be other targets here where fluid had been focused and have been able to lead to concentrations of ore grade. So just to finish, the last 3 slides. This is Tuyubukit. This is the eroded Miocene, upper Miocene volcanic front. This is the present day volcanic front. This is the Aegean Plateau and a large caldera here and 2 volcanoes. And we go to Kagwa Aegean, this here, and it has a crater lake with lots of sulfur, sulfur being released as SO2 or H2S. More than 120 tons per day is the estimated daily flux of sulfur. This is a degassing, this is volatile. This is one of these systems, instead of erupting, is actually a cooking, if you want, rocks at depth, and is in a conditioning situation that potentially could form an ore body at depth. It's exactly the same type of environment. It may not be the same type of, or the same degree of ore mineralization, but is conceptually exactly the same type. We are looking at the surface, a hot, very acid crater lake, pH around 0. And if you look, if there was a very nice PhD done in the 90s here by Del Mel, and if you look at the sediments and at the products that would be in equilibrium with these waters, we are talking about copper, and bismuth sulfides, just like energite, barite, like we saw at Acaigua, tin concentrations, and sediments of native sulfur. So they concentrate, what they do, they concentrate those fumaroles with high concentration of sulfur into these tubes, and that helps precipitate, that helps concentrate sulfur and keep a higher temperature to keep it to liquid. And then they just let it cool and break it into pieces and take it to a local sugar refinery. It's actually, Kagwa Aegean has become now a very touristic place in this part of, in the island of Java. And this guy here, Olive Grunwald, and these are his photographs, took spectacular photographs of these gases at night, these sulfur volatiles, these sulfur SO2 emanations burn with a very bright blue light. And this is a video. So here we are seeing the degassing, devolatilization of that magma chamber, and with a excellent potential to leave behind epithermal as well as porphyry mineralization at different depth levels and depending on the conditions as the fluids come up to the surface. So I hope I summarize well this column. What next? Well, this is a very simplified picture. In reality, what we see, I mean, there are some simple systems like Lepanto Far Southeast you saw, but in reality, what we see, and this is a mining district in Peru, Morococha, is that we see many different centers. So there is a porphyry here, San Francisco. There is another porphyry stock here, San Codiciada, Ticlio porphyry, many porphyry centers, and many vein systems, all of them above a magma chamber. So it's like this magma chamber here with many different types of ore deposits, many different variations, depending on the fluids, depending on the local rocks, depending on the evolution of the fluid, the time, etc. And you end up with a cross-section with a variety of, you see, for example, porphyry coppers, 1, 2, 3, 4, skarns here, skarn-hosted sulfide bodies, Cordilleran polymetallic veins, those are equivalent to intermediate sulfidation epithermal veins. So a very complex mixture, mainly because a very very complex geologic setting here with many different types of units, different intrusions, different ages. All of this happens over a period of several million years above a magma chamber again. So I leave it there with the concept of magmatic hydrothermal systems, centers, and then different types of porphyry of ore deposits depending on the local and the local conditions and the evolution of the fluid. And with that, I finish. Apologies for being a bit late.
Okay, thank you very much, Professor Arribas. Are there any questions from our audience?
Do you have any questions?
Okay, if you have any questions, please make sure to use the raise hand button that you can find in Microsoft Teams.
Can you hear me?
I can hear you. I think probably maybe it takes for some. Oh, okay.
Hello.
Hello. Can you hear us? Not. Okay, Dave.
Now.
Okay.
Sorry, I had my volume down. I didn't want the video to sound.
Okay, no problem.
All of a sudden, I thought these guys haven't heard anything. I was talking to myself the entire hour.
No, we heard you perfectly.
So you say this is the first seminar you are doing at Kyushu University?
Actually, I think it is the 5th so far.
I see. Webinar number 5.
Yes.
Good. I hope you guys are coordinating with Akita University, SEG student chapter.
So far, not so much, even though we have some students here who were at Akita University before. Like, for example, David, the president of our student chapter.
I remember David very, very, very well.
Okay, if there's no questions so far, if it's okay, I would like to ask a question. I think on several slides you, I think just now there is a question in the chat. Maybe I will go to that question first then.
You guys are lucky in Kyushu because you have all of these systems there. You have, of course, Nansatsu, Hishikari,
yes.
the volcanoes. If there is one place in the world where all of this makes sense, all of this is real, and at the same time, giving you a lecture on this is kind of silly because you probably have seen it in the field many times. But that place is Kyushu without a doubt.
Yes, we are very blessed here with our environment. Actually, I see there's one question in the chat from, I'm sorry, the name is displayed in Japanese, so I'm not sure if I'm pronouncing it correctly, but from Mr. or Mrs. John. And they ask, thank you for the very informative presentation, Professor Arribas. Good day. I am I am Alex Amoroso. Okay. Hello, Alex from the Philippines. I want to ask if what are the key ingredients to say that we are on the bottom of the porphyry body? Thank you.
I see here the question. I can read it. Alex Amoroso from the Philippines. The key ingredients to say that we are on the bottom of the porphyry body. Okay. Well, I think you mean, do you mean economically? If you mean economically, obviously is when the grade disappears, when it goes below economic grade. And what you see, for example, in the Philippines at far southeast, Goldfield has been drilling deep, and they have drilled deep and they have drilled below the ore zone, is you still see quartz veining. You still see alteration, strong alteration, potassic or even white mica too, below, but not mineralization, not deposition of metals. So there are still, so it's not a lack of hydrothermal brecciation, it's not a lack of hydrothermal fracturing of stockwork formation, is something else. It may be temperature, but you go, that's as far as I have seen. I haven't seen a porphyry deeper where you go into below any kind of hydrothermal evidence. So you know when you are in the bottom because you don't have grade anymore. And in the case of there is a system in California, in Nevada, where they are able to go into the magma chamber itself, and again way below the ore body. Okay,
thank you very much. I hope this answers your question, Mr. Amoroso. There's also another question from Mr. John Fungo. He says, thank you, Sir Arribas. It is such an honor to hear your talk. My question is, do you have any experience or insights on porphyry copper deposits hosted by ultramafic units?
No, I don't. Sorry, I don't have experience. Porphyry copper deposits in the vast majority of cases are not hosted by ultramafic sequences. They are in intermediate sequences, volcanic sequences. So I haven't been exposed to one.
Okay, thank you very much. I hope this answers your question, Mr. Fungo. We have also more questions from the audience. I see some raised hands. Manuel, do you want to ask a question?
Hi, yes, Henrik. Good evening, Professor Arribas. Thank you so much. It's a pleasure to see you again. I'm very happy. My question
How is your sumo? How is your sumo fighting skills?
Unfortunately, I couldn't exercise more here, but I'm looking forward. Thank you so much.
Keep at it.
I have no opponent here. I'm the best in Kyushu for sumo. Anyway, Sensei, thank you so much. I would like to know My question might be basic question. I have seen people talking about satellite porphyry when they talk about epithermal and porphyry deposit, but I've never understood well this concept of satellite porphyry. Could you please
Satellite
explain?
porphyry.
Yes.
So you think you heard about it in the sense of a main porphyry, a main ore body, and then satellite ore bodies around it.
Satellite ore bodies, I think, but
Yes,
I've never understood
and
well.
that makes sense. You see a magma chamber at depth, okay? Everything starts with a magma chamber and fluids being released from the magma chamber, making it up. And if you saw that image of the model, the 3D model from the magnetic data of the magma chamber below Tujuh Bukit in Java, it had many different apophyses, maybe 6 of them. So that visually gives you a good idea what would be a satellite porphyry. So Tujuh Bukit could be the main porphyry, and then some of those other apophyses could lead to a satellite porphyry coming from the same magma chamber. But in reality, what I think it means is simply a smaller one, spatially associated surrounding the main porphyry. But we know that in reality, they are connected at depth. Is the batholith at depth that is connecting them.
Thank you so much.
And epithermal deposits also happen like that. They happen as clusters because you have again, it's a very dynamic environment, and you have fluids coming up through different structures to different vents. If there is a very large, for example, eruption, that may open a diatreme that makes it a permeable unit, makes it convenient for fluids to flow there. So there is clusters, and that means satellites. One is satellitic to the other.
I see. Thank you. I first thought it is like a body that cannot be seen on surface, something like that.
Satellite. No, I think it's a spatial reference.
Okay.
Blind.
Thank you so much.
If you don't see it, we call it blind deposit.
Thank you, Sensei.
Okay, thank you very much, Manuel. I think we have still more questions. Agata, would you like to ask your?
Yes, hello, can you hear me?
Yes.
Okay. Good morning and good evening there, Professor Arribas. So I want to ask about the age of mineralization. Sorry, because maybe before I have like bad connection, so maybe I missed something, but I wondering about the age of mineralization. So is it possible if like the age of mineralization of high sulfidation deposit, or maybe between porphyry and then high sulfidation deposit below than 1 million age? Because
So,
like there's a
go ahead.
so it says about like very young age. So I just wondering about the age of mineralization. And
sorry, yeah. Agatha, you mean, is it possible that the high sulfidation epithermal is what? What was specifically the question on?
Yes, is it like possible if the age of mineralization, the time of mineralization is like below 1 million age, or what the time of usually the time of mineralization? Okay.
Agatha, do you mean how long it takes to form the deposit, 1 million or less, or can it be younger than 1 million years, the deposit?
Yes. Is it possible if younger?
Okay, yes, definitely. Look, I don't know for a fact that below Kawaijen in Java, there is a high sulfidation deposit being formed. I don't know. But the environment is completely permissible. And there are many hot springs, hydrothermal springs in the Philippines, in Japan, that are very acid. And those also have the same conditions. It's completely permissible that they have an ore-forming deposit happening right now. So what we see in the past is, what we see in the present explains the past. And that means that what we see in the present, in reality, one of those systems will be forming an ore deposit, an epithermal deposit, without a question. How long it takes, if the question is how long it takes, it may take very little time. It may take only tens of thousands of years to form one of these deposits. It may take a few hundreds of thousands, but it doesn't take millions of years. But if you have a magma chamber, you have different pulses of magma, of magmatic hydrothermal fluid at different times. So an area, a district, a mining district can be the results of pulses of magmatic hydrothermal fluid over a few million years, each one shorter, each one short. But altogether, a few million years of an active magma chamber, a district.
Okay. Thank you for the explanation, Professor Arribas.
Okay, thank you very much. It looks like we are coming up against our time limit, but perhaps there is time for one more question. And we have actually one more question in the chat, if it's okay to you, Professor.
Absolutely. I'm here to help.
Okay, this question comes from Saifuddin. He says, thank you very much, Professor Arribas, for the comprehensive presentation. I am Saifuddin from Kyushu University. I would like to ask your opinion about geothermal energy point of view. Some companies / countries are now examining the extraction of geothermal fluids from active volcanoes, which contain much magmatic fluids that are consequently acidic and rich in metals. Do you think this can be a future for metal resources? And if so, what would be the challenge?
A good question. Very good questions, all of them. I don't think it will be. It will have an impact on mineral resources. The metal. First of all, this, as you say, very acid, with a large magmatic component. They are very difficult to handle, as far as I know. They are excellent for. They might be excellent getting to very high temperatures, supercritical fluid. They might be excellent for more efficient energy generation. But I doubt they will be important for mineralization, because the fluxes are not, the metal flux is not that big. So in addition to the technological difficulties and the risks inherent in drilling into magmatic hydrothermal systems of high temperature, the economic reward is unlikely to be worth that kind of activity. Doing it for energy, for more efficient energy production, yeah, I'm sure they are working on it.
Okay, thank you very much. I hope this answers your question, Saifuddin. Professor Arribas, we are, I think, already over the time limit we have set initially, but do you happen to have time for one more question that just popped up in the chat? Okay, so this question comes from Aruga Michitaka. He says, thank you for your presentation, Professor Arribas. I have one question. Does the ore grade change through the formation temperature decrease of ore body in residual silica of high sulfidation epithermal copper gold deposits?
That's what, good question too. That's what we believe. I believe that this cooling of the fluid. The vaggy silica, the residual silica is a very porous rock. So it may contain cooler groundwaters, and that helps also cooling the main effect must be very likely is cooling of the magmatic hydrothermal fluid. I agree. Which is not the same as in low sulfidation environment, where is boiling of the fluid. But to be honest, I don't have absolute evidence. I'm sure both of them, phase separation will have some role, mainly cooling, we believe.
Okay, thank you very much. I hope this answers your question, Aruga. So since we are already now at the end of this webinar, I will to the end give the word to our president, David, who wants to say some things in the end. And also thank you very, very much for your time and your presentation, Professor Arribas. It was a real pleasure.
My pleasure. Pleasure is all mine.
Thank you very much. David, your microphone is muted.
Been talking. Hello, I was saying this is David. Thank you all for coming, and I would like especially to thank Professor Arribas for being with us today and for this interesting talk about magmatic and hydrothermal systems. I think we don't see each other for two or 3 years, and Sensei seems to be still sharp. I would like to take this opportunity to inform that our next webinar will be held on April 21st, and we'll be hosting Professor Richard Goldfarb from the Colorado School of Mine. Professor Goldfarb is one of the top researchers in the world if we are talking about gold mineralization in metamorphic terrains. And some of you might call these mineralization as orogenic gold deposits. So he will be talking about these issues and others. So please stay tuned as we will share the details later. Thank you very much once again for being with us, and thank you, Sensei, for this interesting talk. Thank you very much.
Again, the pleasure was all mine. I wish you the very best. And I see that you guys are at your homes, so you are not going to university just like the rest of the world. Wish you the best. Stay safe.
Thank you, Sensei. Don't forget Henrik, the photograph.
Please.
Yes. Maybe actually, yes. Please turn on your cameras for the final photograph. Agata, maybe you can help me since you have already some experience with taking group photographs in Microsoft Teams.
Somebody's in the lab.
Yes, I suppose some people
I know
are.
that guy.
Kedisi is in the lab.
There's an Akita student there. Hello, Paul.
Kedisi is in the lab, I think.
Hello, everyone. Hello, Prof.
Is anybody in the Philippines or everybody's in Kyushu?
There are some colleagues from Philippines I can see. John, for instance, Chelsea. I saw from the.
Oh, come on, Paul.